Welcome back, folks. The last lesson in Chapter 3, looking at pilots again, but this time we're going to look at smart pilots. So these are pilots that do account for the wind. So we're going to plan to let the wind push us to our destination, a lot like a smart boater plan to angle upstream and let the current push them downstream to their destination. Here we're going to point upwind, if you want to call it that, and then let the wind push us to our destination as well. So we're going to try one still using the airplane assignment map on there. We have a pilot flying from Penticton to Vernon, and they do account for the wind. So we need to start actually by measuring some stuff off of the map. So a slightly different order compared to what we did with the crummy pilots. So if we head to the aircraft assignment, you will see that there is already a dot on Penticton, a dot on Vernon, and a line in between. So what we need to do to get this question started is figure out what the track is. So we need the actual direction, angle between Penticton and Vernon. So on top of Penticton, you want to draw a compass crosshair, compass rose, and again, what you're going to do this time is lay your compass on there, or your protractor, I should say, like that. And I would measure this angle. Always measure off the horizontal. I think you'll find that easiest. So I want to know that angle. And I will sort of do the same thing. You can't see me doing it, but I am. To me, that looks an awful lot like 75 degrees. And that would be 75 degrees towards the north, away from the east. You don't have to label this on your map if you don't want to. We're going to put it on the assignment or on a piece of paper. That's the angle I want. So 75 north of east is the actual path that this airplane needs to take. It's a smart pilot. So 75 degrees north of east. We have to make sure that happens. We also need to measure the distance between Penticton and Vernon. So back to the map. You're simply going to lay your ruler on top here and measure how many millimeters it is from Penticton to Vernon. And if I try that out, you can't see me doing it, but if I try it, it looks a lot to me like about 97 millimeters. There is some uncertainty wrapped in there. You might measure 96 or 98 or 95, that's fine. I'm going to call it 97 millimeters, 9.7 centimeters. 97 millimeters, which is equal to, in real life, 97 kilometers. So, we measure on the map first. Now we can start our diagram. We know that we're flying north and east. So to have a nice big diagram, I want to go sort of down and to the left of my page here. So I'm going to have this represent Penticton. So there's my Penticton spot, and I'll mark that with a P for Penticton. And we're going to have this pilot fly at 75 degrees north of east. You don't have to measure with your protractor, but make the angle look sort of like 75. So maybe something like that. And we want to really carefully label that. 75 degrees. And I want to even go and put that extra little arrow in there, touching that line, just so I don't get things mixed up in that corner. So the top of my vector there is going to represent Vernon. That's where I have to get to. So I'm going to put a star. Star representing my destination, and I have to make sure we get there this time. So I guess the question becomes, how do we get there? Well, we mentioned that boaters angle upstream. In this case, pilots are going to angle upwind. So we know the wind is going this way, to the left, west, at 50 kilometers per hour. So what I'm going to do is actually aim for a magic spot to the right of my destination. Maybe something like that. And if I'm a smart pilot, I'm going to point my plane upwind or to the right, and we're going to take off. When you do that, you hit the throttle of your airplane, the plane goes 200 kilometers per hour, but while that's happening, the wind is going to push that plane to the west or to the left at 50 kilometers per hour. But that actually works. It's going to take us right to our destination. So we're going to let the wind push us right to our destination. Want to add in those compass roses in all three corners, because just like with crummy pilots, we are going to have to play that sort of Z-shaped game. The two things I guess we're looking for in this diagram, just to finish labeling it, we need to figure out the actual speed to our destination, which is the ground speed. That will always be unknown for a smart pilot. So your smart pilot, you'll always have the unknown vector be the one pointing to your destination. Nice to label it with a star. And then we need to figure out this angle. So we're trying to fly at 75, but we want to know how many degrees we have to sort of bend into the wind or bend upwind. So those are the two things we need to find. Before we get going here, I can tell you that a smart pilot, S for smart, S for sine law. You only use sine law for smart pilots. You don't use cosine law. That was reserved for crummy pilots. So I like sine law, so I like this one a little bit better. In order to run sine law, we need to have an angle and its opposite side where we know both of them. So here's where we play the alternate interior game again, that Z shape. And you have to be really careful in this corner when you label it. This extra little arrow helps me see that the Z is running up the blue line, not the green line. So that's my Z shape. And that means if this corner is 75, then so is that one. Which is kind of weird because it's not an angle inside of the triangle, but it's going to help us get one. So that means this was 75 out here. Now, what I do want maybe is the next door neighbor angle. Maybe I can get this one right there. Remember that angles on a line add up to 180. So I can actually get that angle sitting right beside it with a 180 minus 75, which is 105. And that's perfect because look what we've got. We've got some opposites that we can use to run a sine law. Exactly what we want. So I'll get rid of those arrows so things don't get too jumbled. We have a sine 105 opposite at 200 and a sine theta opposite at 50. You will have to second function or inverse sine in order to get the actual angle and not just a decimal. So cross multiply and divide, maybe I'll show that again. Sine law is pretty slick. Multiply diagonally, divide by the leftover. 50 times sine 105, close the bracket, divided by 200. Gives me a decimal, that's good. Second function sine or inverse sine that decimal. Looks like 14 degrees on the nose. So theta is equal to 14.0 degrees. Now, that number on its own, not that useful to us. What we want here is the angle to this line. That's the heading. That's what I'm really looking for in this question. We know the track is 75. We're actually going to have the plane move along the blue line. But we have to know at what direction to point the nose of the plane, which is the green line. And you can see here that 75 is to this blue line, and then we've actually cut through the 75. We've backed off a little bit. So that means our heading is going to be the 75 minus 14. And this is not always a subtraction when you're finding your heading. If our green line had gone like this, we would be going an additional 14 degrees, we'd be adding. So it really is diagram dependent, and you have to do a good job making a clearly labeled diagram so you can see what's going on in that corner. So 75 minus 14. 66 degrees. Nope, sorry. Nice math, Heinrich. 61. Sorry. Degrees, and we have to put some direction on there. So it's actually pretty darn easy. It's the same as it was before. It's still north of east. So that tells us that we need to point at 61 degrees north of east in order to actually fly at 75. And that's because of the wind. So one last thing to find in this picture is the actual speed, the ground speed of the airplane. And if we're going to do that, we need to know this corner of the triangle. Currently we don't have it, but I've got the other two corners. Remember, the angles in a triangle add up to 180. So 180 minus 105 minus 14.0. Hey, look at that, 61 degrees. And you might be going, oh, now I see it. There's actually another Z in here. And it's this one. You know that this corner was 61 degrees north of east, which means this corner of the Z has to be 61. Now, you can't always play another alternate interior game, so I'd actually recommend doing the 180 minus the other two angles. That's your safest bet. But this does work some of the time, so if you see it, fantastic. Let's set up our second sine law calculation then, and we will solve for side V. We've got sine 105 over 200. I'm going to stick with that known pair. And now we've got a sine 61 over V. We can do that slick little cross multiply and divide. No second function required because we're looking for a side length. Let's try this on the calculator so we don't bugger it up like I did previously. 181 kilometers per hour. And that's our ground speed. And that fits the triangle. Always use your number sense. We can see that the 200 is the longest side, so we have to be a little bit shorter than that. That seems to work. Just like the crummy pilots, once we've got that information, we want to use d equals v times t to figure out your time of flight. We measured the d at, what did we have, 97 kilometers. We're always going to use the ground speed for the velocity, so that's easy, the one that you find, 181 times t. And here, this calculation is in kilometers per hour and kilometers, so that means our answer is going to be in hours. So 0.536 h for hours. And what I'd like you to do here as well is find it in minutes, because if you're a pilot and you come on the PA system and you tell people that your trip is going to be 0.536 hours, most people are going to have no idea what that is. So multiply by 60 to turn it into minutes. Much better. 32.2. Now people understand how long this trip is going to take. And again, that was a little multiplication by 60. So that's just to help people out so they're not confused by some decimal number of hours. Now the last calculation here, really important for a pilot, is fuel consumption. So pilots actually have to do this calculation before they go on a flight, and it is the rate at which the plane uses fuel multiplied by how long you're flying for. And this is the same information as on your assignment. We're going to go with this plane consuming fuel at 30 kilograms per hour. So we're going to measure mass instead of volume. So 30 kilograms per hour. I'm just going to show units so we can see which of our times to use. Multiplied by, if we're kilograms per hour, we want hours. 0.536 hours. And then our hours cancel out. We get our answer. 0.536 times 30 16.1 kilograms. Oops. There we go. There's the minimum, I guess, amount of fuel you need to put on board. So that information is actually one of the Smart Pilot questions on your assignment. So we can actually take all of that information and go back and put it into your assignment. So if you flip to that assignment, you will see that for Smart Pilots, there's actually 6 trips that you have to do. But once you get going, this goes quite quickly. You have to trust me. We just did number 1 together. So if you go to the last page, the first table is stuff from the map. So these are your measurements that you're taking before you can get going. So we measured the actual track between Penticton and Vernon at 75 degrees north of east. And it was 97 millimeters, which means 97 kilometers in real life. We then did all those calculations. The heading, just to make sure I get these right, the heading we found was 61 degrees north of east and the ground speed 181. So let's fill that in. 61, 181. 61 degrees north of east, 181 kilometers per hour. Do make sure you get the north of east in there, because if you just put 61, there's actually 8 of those on a compass. There's 61 north of east, 61 east of north, 61 south of west, 61 west of south, and so on and so on. There's 2 per quadrant on your compass rose. This is also looking for the time in hours and minutes. So I think it was 536 hours, which was about 32 minutes. And that gave us 16.1 kilograms of fuel used. So you've got 5 more to try. It tells you all the different legs of your trip on that 3rd page. And you will notice on your map that there are dots at all of those places. So it's easy to find where they are. You may need to draw some lines between them. That's all. So 5 more to try. Give those a go. If you get stuck, get in touch with me. And feel free to take pictures of your triangles, your diagrams, and send them my way so I can look over them. Don't forget that your success is going to come from a nice diagram. And a nice diagram requires 1 per page, nice and big. Got to put arrowheads on those vectors, and make sure you've got your 3 compass roses, 1 per corner. Help yourself see those alternate interior angles. So give those a go. Once you get going, it goes quick. Again, trust me, happy flying.